Now that we have constructed the control flow graph, we can begin to use it for analysis of our program. So the purpose of using this control flow graph is to statically extract information about the program at compile time. So the first thing we want to do is we want to reason about runtime values of variables and of expressions in every possible execution, because this is the basis to enable optimizations. And we will first illustrate this by actually finding the live variables inside of our program. So what is liveness? We've already seen dead code as an example, so liveness extends this principle a bit. So a live variable is one that holds a value that may still be used at a later point. So we have at least one possible execution through our code when we look at a value of a variable at a certain point in time where this value is still used after our current instruction. So on the other hand, a dead variable is a variable for which we can guarantee that it's no longer used after that point of the program we're currently looking at. So until its next assignment, obviously, because this is usually when the use of a variable ends. So this means in turn that we are searching for ranges of instructions of our program where variables hold values that are actually relevant to the execution of our program. And in order to find these ranges of instructions, we need to define so-called program points. And these program points are locations inside of our program that define a start or an end of a range for such a liveness of a variable. So values of variables in our program are changed by the single instructions we're executing. Since we want to capture how the state of variables is changed through an instruction, we need to consider the state of a variable before we execute that instruction, and we need to consider all the changes to variable values and liveness that has happened because we have executed the instruction. So what we have to do is we have to consider the point before the execution of an instruction and as well the point after the execution of an instruction here. So we can extend this to basic blocks, obviously, and for basic blocks, these point before and point after are the blocks after the predecessors and before the successors of the basic block we are currently looking at. So let's take a look at our previous example for which we have constructed our control flow graph. So using these dashed lines here, we mark all the before and after points here. So for example, we have a before point before we enter this if condition here, and we have another program point after it. Then we have a program point before it, but also whatever comes out of if C in terms of variable state is also arriving at this program point here that is located before the start of our final instruction here. And so for all of our instruction, including the instructions inside of our basic blocks, we have program points that define a before and after condition for each of our variables. And the question is now, how can we actually make use of them? So when we have defined program points, we need to consider two different things. The first thing we need to consider is how does an instruction affect the state at the points immediately before and after it. So an instruction can invalidate the liveness of a variable, or it can create a new liveness for a variable here. So in other words, generally, what is the effect of this instruction we're just considering at the moment? And the other thing we need to consider is how does state propagate between the program points? So in other words, what is the effect of control flow on our variable state here? And if we can tell at one point in our program which variables are actually live, then we can compute which ones are live given the neighbors of that point we're just considering here. So which instructions actually affect the liveness of variables? Now, first we can have a use of a variable. So we have a variable here that's mentioned on the right-hand side of an expression like b in our example here. And if a variable is used in this expression, then it must be kept at the preceding program point. So we know that when we read a value of a variable b here, that it has to be live at that program point before we enter this instruction here. On the other hand, if we define a variable in an expression, like our variable a here, then we know that the previous value of a that might have been live until this point here is no longer needed. So a will not be used again, the previous value of a, because we override it here. So if a variable is defined in an expression like our variable a here, then we know it was dead at the preceding program point here. And of course, like with all static analysis, we want to do this systematically because we want our compiler to be able to do this for us. So we do this by defining sets of variables here. So for a given instruction I, we define two sets of variables. So we define an inset of variables for an instruction I, which is a set of live variables at the program point before we enter our instruction I. And we also define an outset of our instruction I, which is a set of live variables at the point after we have executed our instruction I. And we can extend this naturally to basic blocks. So the inset of a basic block B is the set of live variables at the point before our basic block B, and the outset of our basic block B again is a set of live variables at the point after we finished executing our basic block B. So if we have two instructions I1, which is the first instruction in our basic block B, and I2, which is the last instruction in our basic block B, then we know the inset of our basic block B is equal to the inset of the first instruction, and the outset of our basic block B is equal to the outset of our last instruction in our basic block. So we know all variables that are used by an instruction have to be live before the instruction can use them, because otherwise they would not contain a valid value anymore. And we also know that variables that are defined by an instruction can no longer be live at the last point before this instruction. So we can actually define a relation here. So the set of variables that's live before an instruction can be constructed by considering the set of variables that's live after an instruction. And from this set, we remove the variables that are defined by the instruction, and we add the variables that are used by the instruction. Or, in a shorter term, the set in of an instruction I equals to the set out of an instruction I, from which we remove the defined variables which are defined in this instruction I, and we add to this inset the set of variables that are used by this instruction. And now we need to consider control flow. So all variables that are used along the path of any successor of our basic block, and remember we can have more than one successor for a basic block, for example if we have an if condition at the end of our basic block here. So all of these variables that are used along the path of any of the successors of our basic block must be live, because we cannot know which of the passes is taken, so we have to take the worst case assumption that we can take, for example, both passes after an if instruction. So since we never know which path we'll take, we need to have this safe conservative assumption here. So when we have a situation where our control flow splits, then the live after set can be calculated as the live before set of successor number 1, and we add to this the live before set of successor number 2, plus possibly any further successors we might have in our control flow graph. For example, for a switch statement, we might have more than 2 successors. Or we can formulate it in a more formal way here. So the outset of I is the inset of the first successor here, and we add to this set the inset of the second successor when I1, I2 here are successors of the instruction I we're currently looking at. So in these formulas we've constructed just on the previous slides, we've always seen that we define the outset and the inset here, and we have a relation. And we've seen that in these formulas, liveness flows backwards. So we define the inset of an instruction or a basic block in terms of the outset. So this means to start our analysis, we need the outset of a certain basic block, and in this case of the last basic block of our program we're analyzing. So in the name of safety, so we want to make a safe analysis here that definitely covers all possible cases, we need to assume that every variable is live until we have found an example where we definitely know that this variable is not live. Because in many of our examples, we only consider partial programs here, so we don't know what happens to variables after this part of our program was executed. So we just have to conservatively assume that this variable might be used somewhere else, so it is live, unless we can prove it's not live in some part of our program. So this results in a final out state, and we use this final out state as the starting point of our analysis, and then we can work backwards through our program until we arrive at a point where we can no longer change any of the analysis, so where all of our ins and outsets are defined as a fixed set, and then we have arrived at a control flow graph which is annotated by this in and out set for variables here. So what we do is we examine our control flow graph in reverse according to, well, we're going against the flow of our program control flow here to determine the insets, starting with the final outset of our last instruction in our program. So let's do a quick walkthrough of our example here. So we start at the end here, so our last instruction in any case is this assignment here, z equals x. And we just have a conservative assumption here that everything is live at the end. So we take a look through all of our variables here, c, x, y, d, and z. So all of our variables are assumed to be live at the end. So the outset of our last instruction here just contains all of our variables here. And now we can go backward. So we consider what this instruction z equals x changes about the liveness of our variables. Now we see we define a variable value z. So this means that any previous value of z is no longer valid here. So it's not live. So we can remove z here from the inset. So our inset that remains for this instruction is now just cdxy. So the next step we're going to take is we follow our control flow path backwards. So there's only one incoming arrow here. So we follow it backward to this if C condition here. So now we first take the simple approach that says, okay, well, the outset of our previous basic block or instruction is equal to the inset of our following one. So we just copy the outset over here to the inset over here to the outset of our if instruction here. And since our if instruction actually doesn't override the value and it reads the value of C, which is already live here, nothing changes between our outset and our inset due to the execution of this if condition. So now the next step again follows our control flow graph backwards. So the only way to enter if we ignore entering it from the start, is to enter it from this arrow here, so from the z equals 1 assignment. So again, we copy the inset of our if to the outset of our assignment here. So this is the same here. And since this assignment here just overrides the variable z with a constant value here, we're not changing anything because z was not actually live at that point in our program flow given our current state of the analysis. So our input state for this instruction z equals 1 is identical to its output state. So now we have our first more complicated case, because now we have two control flows converging, because we have an if condition with an optional then part, or we just jump over it. So let's first consider the left side here. So we have an inset of cdxy, which we copy to the outset of this assignment in our then part of our if instruction here. And then we consider what's happening. Now, there are two things happening. On the one hand, we assign a new value to x, so x is no longer live. And on the other hand, we are reading the values of y and z, so we know variables y and z need to be live before the instruction here, so at the program point before that instruction. So we remove x from the outset, and well, y was already part of the outset, so this is still live, and we add z to the outset because we read its value here. So now we are at the state where we need to converge our two control flows here. So we have a predecessor here with this basic block of two successors here of our basic block here and directly of our basic block down there. So this must assume that the union of the live variables of each successor might be live. So in one case, we would just kill the liveness of x by overwriting it, whereas if we took the other path through our program here, our previous value of x would still be live. So we have to be conservative in our assumption and add our variable x back to the outset of our basic block here. And then we can go backwards through the instructions of our basic block. So this basic block, if d reads the value of d, this was already part of our live set, so we're not changing anything here. The instruction before this reassigns y, so y is no longer live at the inset, but it reads z, so z is still live here. And now we can take a look at our final instruction, x equals y plus 1. So x equals y plus 1 reads y, so y must be part of the inset here, but we are redefining x, so x is no longer part of the inset here. So this is already a list of in and out sets at our program point, and the question we have to ask ourselves, is this all? Is this really complete, or are we actually missing something? So we know that we've covered all points in our program, but we have seen that something has changed. So what we need to do now is we need to repeat from the start to see if all the additional variables maybe we added here or variables we removed from the live sets change anything if we, for example, go through our loop again a second time. And what we can see here is that previously we only had cdxy as the outset, but we have cdyz as the inset here. So we need to add our variable z, because we use it in this instruction down here, to the outset of our if condition. And this is something we couldn't find before, because we entered our if statement from below, from the last instruction here, which redefined z. So for the case of just going through the loop, our previous value of z here is actually still relevant. So we need to add it here to the outset of our if condition. Accordingly, since the if doesn't change any variable assignments, z must be still alive at the input program point of the if condition. So let's see how far we need to propagate this further. Well, we know that the input program point, so the live variables at the in program point, has to be identical to the live variables at the out program point. So we know that z needs to be live here also, and then we can go backward again. So here we redefine z, so we would remove z from the output set, so the input set is one less variable, which then essentially works. So we have to repeat it again and again until we have iterated through all of the nodes, and as long as we figure out something has changed, then we need to take another iteration. And if we now take another iteration and walk through our nodes again, we figure out that nothing changes anymore. So we say we have reached a fixed point in our iteration over our program steps here. So we have found the final set of live variables at each program point in our program. And we can use this to actually then analyze the program, optimize the program, consider which variables have to be kept in registers, which variables we could overwrite in registers, because we know we won't use them again in the following instructions of our program. So this is a simple algorithm. Now, unfortunately, you need to iterate over and over again through all of this to find this fixed point. But in the end, this gives you a precise information and a safe information, because it's a conservative assumption, especially assuming all variables are live at the end of our program, which you can then base further analysis and optimizations on. So what we're doing here is essentially, by defining program points, we are reading between the lines of our program, and we know every instruction that is part of our program implies a constraint equation. So we've seen live before, the set of variables that's live before an instruction is equal to the set of variables that's live after the instruction, without the variables defined in the instruction. And we add to this whatever is used in the instruction. And everywhere control flows join, we have an additional constraint equation because we have to consider the sum of all the live variables of all the successors to actually determine the life after set of wherever the control flow diverges. And this is the basis for a framework we use for data flow analysis, and this framework simply uses different instances of this pattern. So we can have different constraint equations to capture different information, we can have different behavior for splits and joints of control flow, and this follows the type of information we're after. And this may also work forward or backward through our program. So here with our liveness analysis, we've shown you one application of this relatively simple approach to do this static analysis, but we have many more applications, and this is what we'll cover in the upcoming lectures. So we look at a handful of different instances of applying this pattern in our next lecture. So that's all for today's lecture. So in our next lecture, we take a look at more details of optimizations, especially how to do data flow analysis. And if you're interested in more background information, there's a paper you can read, which is already like 50 years old. So this is one of the first papers that described how to do this control flow analysis we have demonstrated in this lecture here. So that's all for today. Thanks for listening. Until next time. Bye.